A powerful solar storm can mess up life on Earth in a catastrophic way. It can leave huge regions of our planet without power, disrupt communication and navigation satellites, damage power grids and data centers. Scientists warn that the next major solar storm could become one of the most devastating natural disasters. And the question isn't if it happens. The correct question is when. And the scary part? This kind of weather doesn't happen in Earth's atmosphere at all. It starts 93 million miles away on the Sun. When the Sun becomes active, we can feel it on Earth. This activity can mess with satellites, GPS, radio signals, and even parts of the power grid. Scientists usually group space weather into three main types: radio blackouts, geomagnetic storms, and radiation storms from the Sun. Each one has a different effect on Earth. Radio blackouts happen when the Sun sends a powerful burst of energy, aka a solar flare, our way. When that energy reaches Earth, it hits the upper atmosphere and disrupts the way radio signals travel. Geomagnetic storms are different. Sometimes the Sun launches enormous clouds of superheated gas into space. These eruptions are called coronal mass ejections. Imagine billions of tons of solar material blasted away from the Sun at a speed of millions of miles per hour. If one of those clouds comes across Earth, it slams into our planet's magnetic field at full speed. The result is a massive geomagnetic storm. We've already seen some serious space weather recently. For example, in May 2024, the strongest space weather event since 2003 hit Earth. GPS systems went through massive disruptions. The US agricultural industry was hit hard, all because modern farming needs satellite navigation to work properly. As for the infamous 2003 event, it completely cut power in parts of Sweden and South Africa. You might be wondering, what will happen if we get something even bigger? Scientists decided to figure out what a true worst-case space weather event might look like. Now, worst case doesn't mean a once-in-a-million-year disaster. Planning for something that rare isn't super useful. Instead, researchers focused on events that could realistically happen once every 100 to 200 years. Rare, but not impossible. When a strong geomagnetic storm hits Earth, it doesn't just affect space. It can actually generate electric currents in the ground too. And since power lines are excellent conductors, those currents can get inside the electrical grid. It's like extra electricity getting suddenly injected into a system that wasn't designed to deal with it. If the currents are strong enough, they can overload parts of the grid. Safety systems may automatically shut sections down to prevent damage, potentially leading to massive blackouts. Whole regions might stay without electricity. But losing power isn't even the worst part. The extra current can also damage transformers, those massive machines that help move electricity across the grid. Some of these transformers weigh hundreds of tons and can take months or even years to replace. This means that even after the storm is over, parts of the electrical network may still remain damaged for a long time. The power grid on Earth isn't the only thing at risk. A serious space weather event will first mess with satellites hundreds of miles above our heads. And we depend on satellites far more than most people realize. They help us navigate, forecast the weather, communicate with relatives and friends all over the world, and track ships and aircraft. During a bad solar storm, many of those satellites could run into serious trouble. One problem is radiation. When the Sun throws large amounts of energetic particles into space, those particles can slam directly into spacecraft. Over time, they can damage electronics and slowly wear down solar panels, shortening a satellite's lifespan. During an especially powerful event, some satellites could fail completely. But there's another huge problem. A solar flare can actually heat Earth's upper atmosphere. When that happens, the atmosphere expands outward and becomes slightly thicker at altitudes where many satellites orbit. The change is tiny, but for satellites, it matters a lot. Imagine riding a bike on a smooth road, and then suddenly someone pours a thin layer of mud over it. You can still move forward, but you'll slow down faster than before. Something similar happens to satellites. The thicker atmosphere creates extra drag, and that drag slowly pulls satellites into lower orbits. If they lose too much altitude, some spacecraft can fall back into the atmosphere and burn up. And it's happened before. In 2022, solar activity caused Earth's atmosphere to expand right after a batch of Starlink satellites was launched. Around 40 of them couldn't maintain their orbits and eventually re-entered the atmosphere. But during a real worst-case solar storm, the situation could become way more dramatic. It could also prevent us from tracking satellites and increase the risk of their collisions with space debris. The next problem is radio signals. Right now, they're constantly passing through the air around you. Your phone, GPS, Wi-Fi, aircraft communications, ship navigation systems, emergency services, all of them depend on radio waves. And a bad solar storm can mess up many of those signals. Solar flares produce bursts of radio energy, and sometimes those bursts become so powerful that they drown out weaker signals on Earth. It's kinda like trying to hear someone whisper while a jet engine is running nearby. None of this means that a giant solar storm would send us back to the Stone Age. Even a worst-case event probably wouldn't be a Hollywood-style apocalypse. But it could create a chain reaction of problems. Satellites could fail. GPS could become unreliable. Flights could be cancelled. And parts of the power grid could be damaged. That's exactly why scientists spend so much time studying space weather. And now, they might have to come up with a pretty cool idea for protecting Earth from powerful solar storms. They proposed something called Storm Wall. The idea is simple. What if we don't just wait for solar storms to hit and deal with the damage? What if we weaken the solar storm before it reaches Earth? The idea is based on Earth's magnetic field. Our planet is surrounded by a giant magnetic bubble called the magnetosphere. It's like an invisible shield that helps protect us from charged particles coming from the sun. Researchers noticed that Earth's atmosphere already helps strengthen this shield. Tiny particles escape from the atmosphere and interact with the outer edge of the magnetosphere. So scientists decided to try to boost that process on purpose. Their plan involves 6 spacecraft orbiting Earth. Each spacecraft would carry materials like barium or lithium. If you release them into space, sunlight would charge those materials, turning them into a cloud of plasma. Plasma is basically a gas whose particles carry electric charges. The sun itself is mostly made of plasma. The idea is that those artificial plasma clouds would form near the edge of Earth's magnetic shield, and when a solar storm arrived, the plasma would help absorb, redirect, and weaken some of the storm's energy before it reaches Earth. According to the team's simulations, the system could reduce the strength of a serious geomagnetic storm by 50%. That would be a really great result. A storm that's cut in half would mean less damage to satellites, fewer communication problems, fewer GPS disruptions, and less stress on power grids. Of course, this is still just a concept. Nobody has built the storm wall yet. Nobody even knows for sure whether it would work exactly as planned in the real world. But the researchers say that the physics behind it checks out. And apparently, modern rockets can indeed launch the equipment we'd need for such a mission. There's just one problem, and it's money. Building and launching 6 spacecraft wouldn't be cheap. Plus, once the material is released into space, it's gone. You can't collect it, refill it, or use it again. The researchers believe that the mission would use about as much material as a dozen large tanker trucks. That's why the price of a truly massive solar storm could be exorbitant.
In September 1859, scientists observed the first confirmed powerful solar flare. The Sun threw a large amount of radiation, energy, and plasma material into space. This was a massive and devastating disaster, but it happened 93 million miles away, so it probably wasn't such a big problem, right? Well, actually it was. A few hours after the flare was spotted, telegraph lines stopped working all over Europe and North America. Some of them sparked and caused fires. People realized that the Sun was not only the source of light and warmth, but also danger. Scientists called that day the Carrington effect. The good news is that this happened in the middle of the 19th century and didn't cause serious problems for the planet. The bad news is that scientists are warning that in 2025, Earth will experience even more powerful solar storms caused by a coronal mass ejection. This is a giant cloud of plasma or charged gas. At one time, the Sun can throw billions of tons of this material into space. Then, all this flies at high speed through space. Some of the material can reach our planet in 15 hours, the rest in a few days. During the journey, it captures and accelerates any charged particles encountered along the way, which increases its intensity and power. And then, this unstoppable array of energy crashes into our planet. It heats the upper layers of the atmosphere, increases its thickness, and disturbs the work of satellites. They slow down and lose altitude. Communication with satellites becomes unstable, GPS is buggy, data is poorly transmitted. Also, solar-charged gas penetrates into our power grids, transformer booths, and stations. It leads to massive failures that ruin the work of the entire technological chain. A powerful solar attack on several power plants can trigger a power outage in a large city. The internet, phones, social services, networks, nothing will work. We may lose connection with each other. Many large companies would go bankrupt, and the planet may face economic crises. These are big problems, but not the most serious ones. Electric plants serve boiler houses and water pumping stations. Solar storms could stop water from getting to our homes. You wouldn't be able to buy groceries in stores without cash. Of course, we can restore all this, but we'll have to live in the Iron Age for a while. But the worst thing is that a prolonged solar storm can suspend food production. For example, this year, a geomagnetic storm caused by solar storms shut down GPS satellites that are connected with modern tractors, so farmers couldn't work. What would happen if such storms happened every day for a year? We would probably start missing many items in supermarkets. Besides, maritime navigation also depends on satellites. Thanks to them, ships calculate the latitude and longitude of their location. If the satellites are damaged, ships may get lost in the ocean. Even whales get lost in the ocean during magnetic storms. Many birds navigate with the help of magnetic field during long flights to the south. So, not only people, but also animals may experience serious problems. Solar storms heat the upper layers of the Earth's atmosphere and thus make the air thicker. The movement of satellites slows down because of this air resistance. They lose altitude, and one of these satellites is Hubble. Yes, the very telescope that provides us with incredible pictures of space. Scientists say that it will fail much earlier because of solar attacks. You've probably heard on the news that solar activity has recently caused electromagnetic storms on Earth. But fortunately, it hasn't affected our lives in any way. The only problem was headaches, high pressure, and mood swings during those storms. It seems like an ordinary thing, but scientists don't have a consensus on this topic. No one has proven exactly how and why magnetic storms affect our condition. Yes, during storms, the planet's atmosphere becomes less dense, and perhaps this affects our blood pressure, like it happens when the weather changes. So people with cardiovascular system problems should be careful. But the effect on our nervous system, fortunately, is quite insignificant. It's possible that when people hear about a coming magnetic storm and feel unwell, they experience a placebo effect. But there's also good news. All these charged solar particles interact with atoms and molecules in Earth's atmosphere. This interaction leads to beautiful northern lights. It's good to spend some time away from your gadgets and look up at the sky sometimes. One of the biggest storms occurred on March 13, 1989. On March 10th, the Sun ejected a gigantic volume of coronal plasma. The amount of that material was the size of 36 Earths. The solar cloud was flying to us at 1,000,000 miles per hour, and a couple of days later, it crashed into our planet's magnetic field. The collision caused a geomagnetic superstorm. People watched some of the brightest and most beautiful auroras in history. The light show covered most of the planet, but after a beautiful performance, problems followed. The solar storm was so powerful that it went through the atmosphere and reached Earth's surface. First, it disrupted the operation of satellites and then damaged electrical networks. For example, it destroyed a transformer at a nuclear power plant in New Jersey. Energy companies in Canada went down because of systems overloading. As a result, about 6 million people in northeastern Canada lost electricity for 9 hours. This was the largest power outage caused by a geomagnetic storm. Yeah, there were more powerful storms in the mid-19th and early 20th centuries, but the planet wasn't covered by so many power grids at that time. More powerful storms may occur in 2025. The question is, will we be ready for them? Careful study of solar activity can help us prepare. If we know in advance about an upcoming storm, then scientists can switch off some systems and turn them on afterward, theoretically. If the activity of the sun increases every year, then we'll have to come up with new, innovative ways to protect ourselves. Who knows? Maybe scientists will cover all our electrical appliances and stations with a layer of special protective material. Anyway, we must do everything possible not to harm Earth's magnetic field, because if this shield disappears, the surface of our planet will resemble that of Mars. But what causes these solar storms, and why do they affect us so much? Okay, imagine a guy with a nice hairstyle who goes to bed. In the morning, his head is a complete mess. The magnetic fields of the sun are similar to this tousled hair. When the sun rotates, these fields burst, get tangled, stretch, and tear. At those moments, they release huge amounts of energy into space. This is not a problem for the sun, as the fields are restored during the process called magnetic reconnection. Such emissions can cause trouble for the planets in our system. When magnetic reconnection happens, several phenomena can follow. One of them you've already heard about. It's a coronal mass ejection. But there's another terrible thing that the sun does, and it's called solar flare. Imagine a bright burst of solar radiation containing electromagnetic waves, X-rays, radiation, and visible and ultraviolet light. During flares, the sun releases an enormous amount of this destructive energy, and it spreads through space at the speed of light. It takes 8 minutes for this explosive wave to reach our planet. Fortunately, we don't get much damage from these flares because Earth's magnetic field and atmosphere protect us. Strong flares can disrupt radio waves in the upper atmosphere and affect the operation of satellites, but it's nothing critical. Another solar phenomenon is called a radiation storm. These are accelerated electrons and protons that move at a speed slightly less than the speed of light. Thanks to Earth's magnetic field, radiation storms don't harm our planet too much, but they pose a danger to astronauts and satellites. These particles can penetrate human tissues and lead to serious health problems in the way radiation does, but only if you're in space or flying a plane in the upper atmosphere.
Whoosh! British astronomer Richard Carrington was observing the surface of the sun through his telescope when he suddenly noticed something strange. There were two patches of very bright and white light. It's 1859. People are outside working on their farms, harvesting the fruits of their labor. Life is different, more nature, less technology. Science is developing. Not even a light bulb is invented yet. It will be invented in 20 years, though. Back then, the astronomer didn't know he was looking at what would later be called the Carrington event, the largest solar storm ever recorded. In fact, this was the first solar flare we've ever seen and reported. And there was so much going on. Auroras, the southern and northern lights, were just amazing. They've been more intense in that year than in the last 160 years. Auroras mostly appear near the Earth's poles. But back then, you could see these perfectly illuminated lights in the sky close to both the equator and the poles. They spread across the sky from everywhere from Australia to Canada. If you happen to visit the tropics like Panama, Jamaica, or Cuba, you could also see auroras. It was spectacular. Luminous waves were rolling up as far as the zenith, and some were even big enough to cast a shadow on the ground. And the colorful displays were really bright. If you were in Missouri at that time, you could normally read a book by the atmospheric light even after midnight. The light was so strong that the gold miners that were in the Rocky Mountains just woke up, prepared their bacon and eggs, and made coffee without further questions. They thought the sun had risen on a cloudy morning, even though it was 1 a.m. local time. But this extremely strong solar outburst resulted in electrical disruptions from Boston to Paris too. And the telegraph lines. There was so much electricity in the air, telegraph machines could send messages from Pittsburgh to New York without batteries. In Paris, even sparks flew from telegraph machines. And now, fears are mounting that there's another powerful solar storm coming in 2025. It could cause massive power cuts and blackouts, as well as cut off internet access in entire communities, maybe even for months or years. Today, we depend on electricity way more than we did back then, not only when it comes to gadgets in our homes, but hospitals and other places where technology is simply necessary. Electricity is essential even for food, as we need electricity to store it. We need it for our everyday things like work and communication. Another solar storm as strong as the Carrington event could cause trillions of dollars of damages here on Earth. It would knock out power for up to 40 million people only in the United States for a few years. What are solar flares anyway? They are the biggest explosive events that happen in our solar system. So, magnetic energy builds up in the sun. Bam! When there's an intense burst of that magnetic energy, that's when the solar outburst happens. This throws off whole waves of energy that move and travel outward. Of course, it impacts other bodies in our solar system, including the Earth. And when these electromagnetic waves interact with the magnetic field of our home planet, a few things happen. First, what we get is that electric currents flow in the upper layer of our atmosphere. They heat the air. It's like the Earth gets its own electric blanket. This is the stage where you can see stunning auroras over polar regions. But it's also when GPS and radio signals get disrupted. As our atmosphere heats, it puffs up, similar to a marshmallow. This adds more drag to satellites in low orbit. It means that as the atmosphere expands, it's pushing satellites back down to the surface of our planet. It also knocks small pieces of space junk off their course. As strong electric currents flow through the Earth's upper atmosphere, they affect strong currents that flow through our planet's crust too. This can mess with electrical conductors that sit on top of the crust, like power grids. They make the network that carries electricity from generating stations to buildings and homes. And this results in power outages in certain areas, and this can be hard to fix. For instance, this happened in Quebec in March 1989. A powerful solar flare burst off the sun. Shortly after that, another burst sent out 1 billion tons of gas directly to our planet. People there experienced a 12-hour blackout. Only a couple of months later, in August, another solar flare burst towards our planet. It was even bigger than the one that occurred in March. It caused damage to microchips across the world and left Quebec in darkness once again. Flares can be more dangerous for the technology we have than for ourselves. In winter 2022, a solar storm knocked a fleet of over 40 Starlink mini-satellites out of orbit. Solar storms often happen at the same time when the sun releases large bubbles of solar material we know as CMEs, or coronal mass ejections. These bubbles can have billions of tons of plasma, which can move at millions of miles per hour. That way, solar storms fire out radiation, whereas CMEs are plasma eruptions. CMEs and solar flares discharge particles and radiation. As they hit the upper part of Earth's atmosphere, they form radio waves. We call them geomagnetic storms. They form new currents and add energy into electrical grids that are usually passive. This way, they threaten to overload them. Take electricity that's coming out of your wall plug as an example. It changes back and forth by about 50 Hz, depending on the country you live in. Radio waves usually broadcast about 85 to 105 million Hz. Gamma rays and X-rays have frequencies of up to 50 quintillion Hz. Solar radiation is the same one your phone uses for power, only a couple billion times stronger and kinda out of control. Researchers believe a powerful solar storm might hit us in 2025. These storms get to their peak, which, by the way, can turn pretty violent, every 11 years. We mostly get lucky because they bypass us, but we can't expect our good fortune to last forever. Now, we have about a 2 to 3% chance for a Carrington-level event to happen in this decade. The shorted electrical grid wouldn't be only a one-time loss, it would take us up to 10 years to recover from something like that. That way, humankind might be set back by nearly 20 years if it happens. All those particles wildly bursting around could cause damage to our satellites. We could lose communications that way. No TV, internet, or GPS. We'd be dealing with very, very strong radiation. There's a possibility people would face some long-term issues because of that. What could such an amount of solar radiation do to our DNA? Especially those that are not protected by the magnetic field of our planet, like astronauts. Humankind can try to protect the internet against the next enormous solar storm. The first thing we can do is to shore up power grids, undersea cables, and satellites against being overloaded. And we can look for methods of predicting such storms in the long run. That's hard because these storms have been happening for millions of years and we've been able to record them for less than a century. Plus, the technology these storms affect is only 2 decades old. At the moment, we can observe the activity of sunspots, which are black patches on the solar surface that tell us it's the area with high plasma activity. And by checking them, we can predict solar storms up to 2 days before they strike our planet. But we can't track them the way we follow hurricanes. Hopefully, we'll be more ready by 2025 to avoid an internetless future. Although, it would be cool to take a break from social media, don't you think?
So, what's going on with all the news about the sun? Some say that the sun is getting angry. Well, what does that mean exactly, and should we be concerned? Frankly, yes, we should be concerned. It's generally not a good thing to get too much sunshine. The ultraviolet component of sunlight is harmful to the skin. That's why humans have adapted a spectrum of skin pigmentation. The more sunlight there is to protect ourselves against, the more pigmentation we need. Big floppy hats and, of course, bottles of high SPF oil-free sunscreen help too, especially for fair-skinned people. But what is planet Earth going to do? First, let's get a good estimate of just how angry the sun is likely to get. The sun usually goes through an active-calm-active cycle every 22 years, with highs and lows occurring every 11 years. Why that happens, no one knows, it just does. There's probably a reason, but scientists haven't figured it out yet. They do know that, with each cycle, the sun reverses its magnetic poles. That in itself is pretty astounding, especially when you consider that Earth hasn't reversed its magnetic poles in the last 600,000 years. Lately, the sun has been extremely calm, the calmest it's been in over 100 years in fact. That's unusual too. The active-calm-active cycle has turned into an active-calm-calm cycle. But that's changing, and it's why we are notifying Brightsiders about what to expect in the coming few years. The terms calm or active or angry refer to the amount of high-energy radiation that the sun gives off. Thankfully, the amount of visible light the sun gives off doesn't change very much. That would be a serious problem. If the sun were to get just 6% dimmer or brighter, the Earth would either freeze or fry. Observing sunspots is the easiest way to measure how active the sun is. The more sunspots that are visible, the more active the sun is. A graph, known as the butterfly diagram, tracks the 11-year period of sunspot activity. The butterfly diagram shows how sunspots disappear regularly from the surface of the sun and reappear regularly in other locations. NASA predicted that the present cycle of solar activity would be calm like the previous one. But it's starting to look like that is not the case. Presently, we are in solar cycle number 25. That's the 25th 11-year solar cycle since 1755, when record-keeping began. This cycle of solar activity is expected to peak in 2025. The Sun has already exceeded the number of sunspots NASA had predicted. So, it doesn't look like this solar cycle is going to be a calm one. It looks like we are going to have some very active sun-blasting radiation on Earth for the next several years. In early February 2022, 40 out of 49 SpaceX communication satellites in orbit above the atmosphere were destroyed by an explosion on the Sun. High-speed electromagnetic plasma gas from the Sun, known as solar wind, caused the Earth's atmosphere to compress, and Elon Musk's satellites lost their orbital integrity and crashed back into Earth. Sunspots look like dark spots on the Sun, but they aren't dark. They're just not as bright as the surface of the Sun. To get a better idea, take a lit 25-watt light bulb and hold it in front of a lit 100-watt light bulb. The 25-watt light bulb will appear dark. That's the same way it is with sunspots. Sunspots on the surface of the Sun almost always come in pairs. This is because sunspots are magnetic storms in the plasma gas of the Sun. One sunspot will be magnetic positive, and the other sunspot will be magnetic negative. Between the two sunspots, which can be many times bigger than the Earth itself, there flows an electric current that carries a fiery arc of ionized gas with it. Solar flares are something else we should be concerned about. They are powerful electromagnetic explosions on the Sun associated with sunspots. As the superhot plasma gas on the Sun churns and twists, it also twists the magnetic field lines in the sunspots. When these lines snap, a powerful explosion releases X-ray and gamma radiation at the speed of light. Visible gases are also released. Solar flares have a classification system according to how powerful they are. X-class solar flares are the most dangerous. This type of solar flare can cause radio blackouts across Earth and harm satellites, astronauts in orbit, and even passengers on high-altitude airplanes. M-class solar flares cause spectacular aurora at the North and South Pole areas on Earth, while C-class solar flares have almost no effect on Earth. But solar flares are not the biggest explosions on the Sun. CME stands for coronal mass ejection, and these are much more massive than solar flares and more dangerous when they're headed our way. As the name indicates, coronal mass ejections are explosions that originate on the Sun's corona. They hurl millions of tons of hot ionized gases outward from the corona. The word corona is derived from the Latin word for crown, and it's the layer of thin bright gas around the Sun's surface. The corona of the Sun is much hotter than the surface of the Sun. The surface itself is about 10,000 degrees Fahrenheit, but the corona is somewhere between 1 to 2 million degrees. The why and how the corona is so much hotter than the surface of the Sun is another major mystery that scientists have yet to completely work out. A recent theory claims the corona is heated by sound waves and the Sun's nuclear reactions make a lot of noise. Project GONG, which stands for Global Oscillation Networking Group, was set up on Earth to monitor the sound waves on the Sun. Cool, huh? Turns out the Sun is ringing or oscillating like a bell. And we have 5 observation sites across the globe. One in India, Australia, one in the Canary Islands, one in Chile, and one in California that keep a constant watch over the 10 million sound waves moving on and around the Sun. Now that the Sun is entering an active phase, we can expect to see more powerful CMEs heading our way. The gases expelled by the Sun are ionized and stripped of electrons by the intense heat. This causes them to form a proton storm that can travel through space at speeds of around 500 miles per second. These positively charged atomic nuclei will mostly be blocked or deflected by the magnetic field that extends around Earth. Our atmosphere is no help against a proton storm, although the last mile of air above the surface of the Earth stops the harmful X-rays from solar flares. The particle wind from the Sun can only be stopped by Earth's magnetosphere. We can look forward to some spectacular aurora around Earth's magnetic poles, and it's very possible that these aurora will extend down to the mid-latitudes when the Earth is moving through a coronal mass ejection. Currently, the United States has a space probe headed for the solar corona. Because the corona of the Sun extends outward for many millions of miles, the Parker Solar Probe, as it's called, is cruising 3.8 million miles from the surface of our star, or about 1/10 the distance to Mercury. The probe is experiencing temperatures of 2,400 degrees Fahrenheit, but it is also kept at perfect room temperature. A 4.5-inch thick carbon composite heat shield protects the telescopes and magnetometers in the probe that measure the intensity of the solar wind. The 5 antennae that protrude into the coronal gases are made of a niobium alloy, which can withstand the extreme temperatures of the corona. The recent double calm cycle of the Sun is a bit concerning when trying to predict how active the Sun will get this cycle. The sunspots completely disappeared for a long time from the entire surface of the Sun. It is as if the magnetic distortions we usually see on the photosphere of the Sun had collapsed into its interior. Intense magnetism is coming to the surface now and breaking through into the corona. The National Center for Atmospheric Research in Boulder, Colorado, is predicting that this solar cycle, cycle number 25, will be one of the strongest ever. The last solar cycle was very calm, with a sunspot count of only 116. The average is 170. But the prediction for this cycle is between 210 and 260 sunspots, which would be one of the strongest cycles ever. We stand to lose more satellites to a stronger solar wind. We can also expect electric grid overloads as the proton storm peaks in 2025. That means we should expect an interruption to our internet services as positively charged protons get into the wires, run into the transformers, and overload them. On March 12, 1989, a powerful CME hit Earth and created absolute havoc with our power grids. Will we experience anything of this magnitude in the near future? Well, stay sharp, Brightsiders. Imagine a giant, immensely powerful storm rotating over your head. You'd be terrified if you could see it. But this storm is invisible to the unaided eye. It isn't your regular hurricane. This intense phenomenon happens in space. Space hurricanes are giant swirling storms that form not in our oceans but up in the ionosphere. It's part of Earth's upper atmosphere charged with energy from the Sun. Space storms look a lot like traditional hurricanes, except they're made up of plasma, supercharged gases, and instead of raining water, they rain electrons. These massive rotating hurricanes appear over Earth's polar regions. Now, think of a space hurricane as a giant funnel or whirlpool of energy spiraling over the polar regions. It's only visible from high altitudes or by satellites. Space hurricanes also produce cyclone-like auroras. Such colorful light shows look similar to good old auroras, but there's a big twist. Space auroras usually spin near the North Pole for several hours, raining charged particles into the upper atmosphere. Hurricanes on Earth are born from warm ocean water and low-pressure areas. They're fueled by Earth's rotation and heat energy from the ocean. Space hurricanes, on the other hand, are created by a different process altogether. They're influenced by magnetic fields instead of Earth's water. When the solar wind, a steady flow of charged particles coming from the Sun, comes into contact with Earth's magnetic field in just the right way, it creates a kind of swirling vortex of energy high up in the ionosphere. It starts spinning, much like how a regular hurricane spins in the atmosphere. Now, let's go all the way back to 2014. That was the first time researchers spotted a massive space storm over the Arctic using satellite data. That hurricane was huge, but at that time, they didn't know exactly what it was. What they did know was that its base stretched over 600 miles in diameter, and it had multiple spiral arms that looked just like the arms of a traditional hurricane. The storm also had a calm eye in the center. There, the plasma was still compared to the fast-rotating outer regions. Some parts of this storm spun at speeds up to 4,700 miles per hour. It's an incredible speed compared to Earth's hurricanes. The team observed the phenomenon for 8 hours. After that, it gradually broke down. Scientists managed to identify this storm as a space hurricane only in 2021, using observations that had been made several years before. Space hurricanes have several distinct features. First, it's cyclone-shaped, massive, bright auroras that can last for hours. Then there's the eye of the storm, a calm, stable center of the hurricane. A space hurricane also creates a circular magnetic field with strong disturbances around it. Plus, scientists mention electron rains in the ionosphere. These rains are what causes those bright, colorful auroras right below the storm. But how do space hurricanes form? To understand this process, we need to first talk about regular auroras, like the northern lights. The sun emits a stream of charged particles, also known as the solar wind, non-stop. And sometimes, this wind brings massive bursts of energy towards Earth. Luckily, Earth has a magnetic field that acts like a shield, protecting us from most of this high-energy solar radiation. But when solar winds are too strong, they can get into the upper atmosphere, especially near the poles. When these particles from the sun hit Earth's magnetic field, they release energy that lights up the sky in the form of auroras. Now, in a typical aurora, electrons from the solar wind excite nitrogen and oxygen molecules in the atmosphere, which then emit light, leading to colorful shows in the sky. Space hurricanes are similar, but they happen at higher latitudes, above the region where auroras usually appear. They create a swirling, cyclone-like effect that looks quite different. Scientists are still studying the exact conditions necessary for a space hurricane to occur. But they already know that, surprisingly, such storms happen during very calm space weather. This is the opposite of traditional geomagnetic storms, which need intense solar activity. Space hurricanes need just the right balance of low solar wind and northward-pointing magnetic fields. And even though these storms are uncommon, they aren't impossible. Hence those unique swirling storms above the poles. When scientists observe the space hurricane over the North Pole, they notice some shocking similarities to hurricanes on Earth. Just like the typical hurricane, a space hurricane has a central area where the plasma is calm. Even more curiously, the plasma in space hurricanes spins in a counterclockwise direction, which is like hurricanes raging in the northern hemisphere. The space hurricane also has multiple spiral arms, just like the ones you can see in satellite images of Earth hurricanes. Plus, the space hurricane doesn't need the strong solar winds that typically create disturbances in our atmosphere. No, it forms in periods of calm, just like how an Earth hurricane can only form if the winds in the atmosphere aren't too disruptive. Now, space hurricanes may be high above us, but they can still affect our daily lives, especially in areas related to satellite communications and space navigation. Those electron rains caused by the storm interfere with radio signals that travel through the upper atmosphere. It can disrupt GPS systems, radio communications, and radar systems. What's even worse, this interference can impact the orbits of space debris or space junk, which is already a problem for spacecraft and satellites in low Earth orbit. The storm's electron rain slightly heats up the atmosphere, which leads to extra drag on satellites and can potentially change their orbits. At the same time, the effects space hurricanes have on Earth aren't as direct and disastrous as those of hurricanes down here. They really don't pose any serious health risk to astronauts or damaged satellites. But researchers say that studying such storms can help improve predictions for satellite operations, especially for flights that cross polar regions. Now, interestingly, scientists didn't set out to find space hurricanes when they spotted one. The discovery was a total accident. It happened when Larry Lyons, a space physicist from UCLA, and his team were looking through satellite data for another study. In this study, they noticed unusually strong plasma flows in the polar cap, the region at Earth's poles where auroras usually don't appear. When they looked more closely, they saw that this plasma wasn't just flowing, it was swirling, creating a circular pattern with a bright auroral spot in the middle. The researchers were intrigued. They analyzed over 300 different space hurricane events that happened over a span of 11 years. These storms appeared most often in the afternoon during summer months. It made the scientists believe there might be certain times and conditions that could encourage their formation. Luckily, with new research tools and techniques, scientists have been able to identify space hurricanes with greater precision. And recently, they've spotted parallel storms happening near the South Pole as well. The most exciting thing about this research is that it might help us better understand Earth's space neighborhood and the way solar energy affects it. Scientists like Lyons believe that space hurricanes may not actually be a new phenomenon. They may have been occurring for a long time, but no one noticed them. Space plasma physicists point out that space hurricanes resemble a phenomenon people observed earlier. It's called high-latitude dayside auroras. At the same time, space hurricanes are much brighter, and they have stronger circular flows, which give them those hurricane-like arms. Understanding space hurricanes could eventually help scientists predict them. It would be useful for planning space missions and making satellites more reliable. Plus, by looking at these storms, researchers hope to create a more complete picture of how auroras behave at higher latitudes. And even though space hurricanes may seem purely like scientific curiosity, they can give us important clues about how Earth's magnetic field and atmosphere interact with the solar wind. And who knows? This understanding might even help us spot similar storms on other planets with magnetic fields. It could offer clues about magnetic storms beyond Earth. The Earth. Frozen and alone, exiled into deep space. Jupiter, the only remaining planet orbiting the Sun. No, it's not a premise for a disaster movie. It's one of many real scenarios scientists explored in their latest simulations. This time, the threat isn't the Sun swelling or a giant asteroid knocking planets into it like a cosmic bowling ball. It's something quieter and possibly already on its way. A recent study examined the potential consequences of a passing star coming too close. One such flyby could send planets crashing, flinging them into space, or mess with their orbits just enough to cause climate changes. But what are passing stars, and how likely is that to occur? Passing stars are normal stars, like our Sun, that move around the Milky Way. Since everything in space is always moving, sometimes stars pass near each other. Usually it's not a big deal. But if a star gets really close, its gravity can tug on planets like Neptune. That tiny tug can slowly change how the planets move, like a ripple spreading through the whole system. Scientists study these close encounters because, even though they don't happen often, they can have big effects over millions of years. They help us understand shifts in planetary orbits and how they may have shaped Earth's past. In fact, one theory suggests that a flyby 56 million years ago is what caused great climate change when Earth's temperature rose by up to 14 degrees Fahrenheit in just a few 100,000 years. That huge temperature jump changed life on Earth, leading to the evolution of some species while causing others to disappear. Even though it's impossible to prove whether there was a flyby a long time ago, we do know that events like this could mess with Earth's orbit in the long run. That's in the past, but what about the future? So far, we know that the solar system will have a close encounter with another star called Gliese 710 in about 1.3 million years. Gliese is moving towards us and is projected to pass within 10,000 astronomical units of the Sun. It won't come close enough to throw planets off, but it could still send icy comets from the Oort cloud our way, like a bored kid tossing a snowball without looking. One might hit something, but probably won't. However, in a recent study, scientists wanted to explore a more extreme scenario. What if a star passed even closer, say just 100 astronomical units from the Sun? That's about 100 times the distance from Earth to the Sun. From our point of view, it's almost unimaginably far, but in space, it's practically brushing shoulders. They ran thousands of long-term simulations covering up to 5 billion years of our solar system's future, and it turns out it doesn't take much. Just one close encounter can be enough to disturb the outer planets, like Neptune, and set off a slow-motion chain reaction that ripples inward. Over time, that gentle nudge can throw the whole system into chaos, a true cosmic butterfly effect. The good news is that even in this worst-case scenario, in 95% of simulations, the passage is nothing to worry about, and all the planets remain in place. However, in the remaining 5%, well, it's one disaster after another. The most frequent casualty in these simulations was Mercury. In nearly half of all unstable scenarios, Mercury ends up on a doomed path straight into the Sun. It's the smallest planet and the closest to our star, so it's especially susceptible to gravitational nudges, whether from the gas giants or from a disturbance rippling inward from a stellar flyby. When Mercury spirals into the Sun, you might think it's game over for the rest of the planets, but that's not always the case. Sometimes the system absorbs the loss and restabilizes, like an orchestra that keeps playing even after one violinist falls off the stage. Oops. Funny enough, Mercury already has a chaotic orbit, the most stretched and tilted of all major planets, and some studies already consider its fall into the Sun in the distant future inevitable. Now, Venus has a slightly better chance in these chaotic scenarios. It doesn't get ejected or swallowed by the Sun as often as Mercury, but it's far from being safe. Most of the time, the instability happens after Mercury goes rogue and disrupts Venus's orbit, nudging it into a slow-motion crash course with Earth or Mars. Even without the interference from field stars, long-term simulations show a tiny but real chance that Venus could eventually collide with Earth just from the way Jupiter affects Mercury. A Venus-Earth collision would result in both planets being completely destroyed. Oh well. A similar fate awaits Mars. According to simulations, in about 0.3% of cases, it either gets flung out of the solar system or collides with another planet. Mars is smaller and lighter than Earth, with weaker gravity, which makes it easier to knock it off track. What's interesting is that even in some cases where Mars is lost, Earth often manages to stay in place. Jupiter happens to be the heavyweight champion of the solar system, the proud owner of its own cloudy belts. Thanks to its massive size and strong gravity, it acts like an anchor, keeping everything else in check. There are 392 scenarios out of 12,000 simulations where all but one planet vanished, with Jupiter being the last one standing. Its stabilizing influence helps prevent smaller planets from going off course, and in some cases, it even helps the system recover after a disruption. Saturn, while less massive, seems to be Jupiter's loyal partner. But models show that when Saturn shifts its orbit abruptly, it can send gravitational ripples, known as secular resonances, straight into the inner solar system, nudging the orbits of planets like Earth and Mars. Finally, the most vulnerable ones are Uranus and Neptune. Sitting at the edge of the solar system, they're the easiest to knock loose, and in many simulations, they get ejected entirely. That loss sends gravitational ripples inward, disturbing the rest of the planets over millions of years. Even a tiny shift by 0.1% in Neptune's orbital distance can throw the whole solar system out of sync. The balance of gravitational forces would shift, forcing Jupiter and Saturn to readjust, which would push the disturbance toward the inner planets, destabilizing everything. Which brings us to the big question: what about Earth? While most simulated models leave Earth untouched, about 0.2% of the simulations end with Earth either colliding with another planet, Venus, or being thrown into the Sun. Out of 12,000 simulations, in 23 of those, Earth ends up as the only one still orbiting. But that's only if we don't include the Moon in calculations. With the Moon included, Earth becomes harder to predict. Our satellite could crash into Earth, get ripped away by a passing star, or destabilize our orbit over millions of years. Once again, this is a worst-case scenario, and while the odds are really, really small, it's not impossible. So, with that in mind, let's entertain the idea and see what would happen to Earth if it were to end up exiled from the solar system. Earth would become what scientists call a rogue planet, drifting through interstellar space with no sun to anchor it. The surface would quickly freeze, with temperatures dropping to hundreds of degrees below zero. But surprisingly, life wouldn't vanish completely. Earth's core would stay hot for billions of years, powered by radioactive decay and leftover heat from its formation. That heat could keep underground pockets warm. Scientists believe that this is the case with icy moons like Europa or Enceladus. Life might cling on in different caves or buried oceans. It wouldn't be a thriving world, but it wouldn't be completely empty either, at least for a while. Just cold, quiet, and alone. A ghost of a once lively world. And somewhere out there, maybe another civilization will look up, spot a faint blue dot drifting by, and curiously start running simulations of what might happen if this blue planet were to get really close, say just 100 AU from their sun.
A solar storm is crashing into Earth like a cosmic tsunami. First, the atmosphere ignites, sparking massive auroras. High-energy radiation slams into the surface, frying power grids, turning lights off across continents, and knocking out satellites. Planes lose navigation, radios go silent, GPS systems crash, radiation levels spike dangerously. Communication collapses, emergency services scramble in the darkness, and chaos spreads as people struggle to cope. Solar particles start to strip away the very air we breathe, slowly peeling off our atmosphere. Soon, Earth will become a harsh and hostile place. That's what solar activity can do to our planet and its inhabitants if we didn't have a protective shield called the magnetosphere. But even with this barrier, we're still in for serious problems. A mysterious 100-year solar cycle may have just restarted, and it could mean decades of dangerous space weather. New research suggests that the unexpected intensity of the ongoing solar maximum may be partly tied to a lesser-known 100-year solar cycle. If the Sun is indeed entering its villain arc, solar activity could spike even further in the coming decades. It means more solar flares, more chances of them messing with satellites, and way more of those crazy northern lights people keep posting on Instagram. Sure, not everyone's buying it. Some space nerds want more proof before jumping on this solar hype train. Let's break it all down into detail first. The Sun goes through a kind of mood swing every 11 years. This is called the solar cycle. It starts off at a solar minimum, which is pretty chill, then slowly gets rowdy. We're talking sunspots, solar flares, and other fiery drama. Once we reach solar maximum, the situation starts to calm down again. The Sun gets sunspots, dark patches on its surface, like the freckles we humans have, when its magnetic field starts flipping out. Literally, the Sun's magnetic field completely flips during peak solar drama. Scientists track how many of these spots show up to measure how spicy the Sun is getting. But wait, plot twist, there are other cycles too, like the Hale cycle, which occurs around every 22 years. This cycle controls how magnetic fields move across the Sun. Plus, way back in history, there were moments when the Sun basically went on Do Not Disturb mode. During the Maunder minimum, our star was basically in sleep mode for 70 years. In other words, the Sun might be entering a new extra phase, and things could get dramatic. On the bright side, that means more auroras. At the same time, it could also cause issues for satellites, GPS, and other stuff we rely on. Ugh, let's just hope it doesn't mess with YouTube. This extra phase is called the Centennial Gleisberg cycle. It's basically the Sun's once every 100 years I do something weird moment. Scientists think it messes with how intense sunspot cycles get. No one has fully worked out how this cycle works yet, but some low-key sloshing of magnetic fields inside the Sun might be causing it. Yep, I did say sloshing, like a giant cosmic smoothie. A recent study from March 2025 claims that the CGC might have just hit restart. That could explain why this current solar maximum, the Sun's drama phase that started in early 2024, is being so weird and unpredictable. How did researchers figure this out? They looked at something called proton flux. Basically, it's how many positively charged particles are flying around in Earth's radiation belt. There are 2 of these belts, shaped like donuts that wrap around Earth, full of particles from the sun. The thing is, when the sun is active, our upper atmosphere swells, which makes the inner radiation belt lose some of those protons. And when the sun is chill, proton numbers go up again. So those protons have been increasing for like 20 years, but just started to drop in the past year. Which basically screams CGC has just hit minimum. Time for the sun to crank it back up. The data came from NOAA satellites that flew through the South Atlantic anomaly, which is like the Bermuda Triangle of space. It's this bizarre zone over South America where Earth's magnetic field is weaker and space radiation gets closer to Earth. This area is perfect for observing proton activity without sending a satellite into the actual danger zone. So, right now, we're probably nearing the end of the sun's current chaos phase, aka the peak of solar cycle 25. Back in May 2024, it hit us with one of the craziest geomagnetic storms in 500 years or so. And yes, that means super bright auroras lighting up skies all over the world, even in places that usually only get clouds and vibes. But the scariest thing? This wasn't supposed to happen. During the last cycle, the sun was oddly calm. So NASA and NOAA looked at that and thought that the next solar cycle would probably be the same. No biggie. Well, they were wrong. And they even admitted it. Now, scientists think that SC24's quiet phase was because of the Centennial Gleisberg cycle being at its low point. That probably made it the quietest sunspot cycle in 100 years. So now that SC25 is lit again, pretty literally, it might just mean the sun is back to doing what it normally does, being a little chaotic and wild. Recent studies think the CGC minimum is finally over. That would explain why the current solar activity is turning up the heat, and why the last one felt like a cosmic snooze. An even cooler thing is that a 2024 study used AI to analyze sunspot patterns and found that CGC might be messing with our forecasts more than we thought. And if this long-term mood swing of our star is really back on the rise, future solar cycles could be just as wild as the one we're in now, or even wilder. After all, we've just passed the CGC's low-energy mode, and we won't hit the next maximum for another 40 to 50 years, around solar cycle 28. That's a few decades away, but the sun's already throwing tantrums. The scariest part is that future solar activity might be twice as intense as what we're seeing now. You might be wondering right now, why should I care? Well, because when the sun freaks out, it messes with our stuff, especially in space. Satellites get dragged out of orbit because Earth's upper atmosphere literally puffs up like a marshmallow in a microwave when solar activity spikes. And this has already happened to a few spacecraft recently. And with tons of private satellite mega constellations like Starlink and its squad, the risk goes way up. There are some, even though those are few, that might not be ready for a full-blown sun rage event. Time to wear SPF 100 for your satellites. Astronauts are also at risk. More solar flares mean more radiation and more danger for humans in orbit. At the same time, more space tourists and missions mean more people potentially in the sun's cosmic splash zone. At the same time, not everyone is buying into the whole CGC is back and ready to party theory. Some experts say it's a cool theory, but we shouldn't get carried away. The thing is, the proton flux, those space particles we've been watching, only started dropping last year. That's not a lot of time. It might just be a short-term dip, like the sun sneezed and now everyone's freaking out. Also, we've only been able to track this stuff properly for 30 to 40 years or so, which is basically nothing in sun time. So there's no solid before and after data to compare CGC cycles and say, yep, this is definitely a pattern. Plus, the CGC itself is kinda mysterious. Like no one can fully agree on what it even is, how it works, or how much it actually messes with sunspot cycles. It's like the Bigfoot of solar science, blurry, weird, and causing drama in group chats. But even skeptics admit that the new study is interesting and well-intentioned. and that it might help us predict future solar cycles better. We just need more time, more data, and better definition of the CGC before we treat it like the ultimate weather app for the Sun.
On July 23, 2024, Europe's Solar Orbiter spacecraft observed a super-powerful solar flare erupting from the far side of the Sun. This flare wasn't the most extreme ever recorded, but still, we got extremely lucky this time not to get fried by it. Such solar flares often cause long-lived, raging radiation storms, and if such a storm moves in the direction of Earth, it can lead to worldwide blackouts. Before we go deeper into details of that potentially disastrous solar flare, we need to figure out what exactly this solar phenomenon is. Solar flares occur because the magnetic fields in the atmosphere of our star are moving non-stop. When the Sun is approaching its solar maxima, and that's the most active period of its 11-year-long cycle, which is, by the way, exactly what's happening now, its magnetic fields get more and more tangled, making our star look like an enormous ball of tangled rubber bands. They loop around, cross over one another, cut one another off, and then reconnect. Ever seen iron filings sprinkled on a bar magnet? These filings line up along the magnetic lines of force. Like that, the hot plasma on the surface of the Sun is at the mercy of the magnetic lines of force. Sometimes, when the magnetic fields interact with each other, some plasma gets disconnected from the fields, and its particles accelerate to immense speeds and send powerful radiation to space. That's what a solar flare is. Other times, our star throws off massive amounts of matter. Those events are coronal mass ejections, CMEs. Just one CME can contain as much as 20 billion tons of material. If that material were rock, it would create a mountain about 2.75 miles across and almost a half a mile tall. The ejected material often travels at a speed of over 1 million miles per hour. Solar flares and CMEs are the most powerful explosions in the solar system, releasing unimaginable amounts of energy. Solar flares have their own classification according to their strength. The smallest and weakened ones are A and B class. Then there are C and M class solar flares, and the strongest are X class flares. A number from 1 to 9, and in some cases a larger one, accompanies each letter. That's similar to the Richter scale for earthquakes. A and B class flares are too weak to affect our planet. As for C class flares, they may have small, noticeable consequences. M class flares can cause short radio blackouts at the poles and weak radiation storms that can still harm astronauts. But the most dangerous of them all are X class flares. These are flares more than 10 times more powerful than X1. That's why the classification of X class flares can go higher than 9. Now let's get back to that recent solar flare. It was X14 Class 1. Now, we already know that it means it was an extra strong flare. Other large flares astronomers have detected recently include an X12 solar flare that happened on the 20th of May and an X10 flare that occurred on the 17th of July. All of them have come from the backside of the Sun. If we talk of the Earth side of our star, the largest solar flare that has been recorded so far within this solar cycle happened on the 14th of May. It was an X8.7 flare that led to radio blackouts, and a strong geomagnetic storm leading to magnificent auroras all over the world occurred a few days earlier. Powerful coronal mass ejections accompanied this storm. As for the July X-class flare, it was so powerful that it could have ended up tragically for us. Luckily, all that magnetically charged plasma blast that accompanied the flare didn't travel in our direction. If it had, it would have been quite the solar storm. Auroras would have been incredibly impressive and a wee bit terrifying in their magnificence. But at the same time, such a dynamic blast of energetic particles hurtling our way could have caused major technological problems and electrical blackouts, like the event in 1989, which severely harmed Quebec's power grid, or a much earlier catastrophe that still managed to cause a lot of harm to the world. I'm talking about the Carrington event, which occurred in 1859 and was the first documented solar flare affecting our planet. It happened on the 1st of September and was named after Richard Carrington. the solar astronomer who witnessed the flare through his own telescope and sketched the sun's sunspots. According to scientists, that flare was the most powerful documented solar storm over the last 500 years. The Carrington event triggered auroras that were visible as far south as the Caribbean. It led to severe interruptions in telegraph services all over the world, even shocking some telegraph operators and sparking fires after discharges from the lines ignited telegraph paper. Another major solar flare that erupted on the 4th of August, 1972, destroyed long-distance phone communication across a few states, including Illinois. This event even made the American Telephone and Telegraph Company redesign its power system for transatlantic cables. Now let's move to March 1985, when two superpowerful CMEs triggered a geomagnetic storm, which, in turn, set off a power blackout in Canada on the 13th of March. This blackout left around 6 million people without electricity for 9 hours. It is said that the flare disrupted electric power transmission from the Hydro-Quebec generation station and melted a few power transformers in New Jersey. And still, this solar flare was nowhere near the power of the Carrington event. The Bastille Day solar storm took its name from the French national holiday because it occurred on the same day, on the 14th of July in the year 2000. It was an X5 class event that caused some satellites to short-circuit and resulted in radio blackouts. It's still one of the most highly observed solar storm events. From October to November 2003, our star unleashed a series of large solar flares and coronal mass ejections, and they did reach Earth and slam into our atmosphere. Those solar storms, also known as Halloween storms of 2003, caused aircraft to be rerouted, impacted satellite systems, and led to power outages in Sweden. Besides, the Solar and Heliospheric Observatory couldn't fulfill its functions during this solar onslaught. On the 28th of October 2003, the Sun sent a whopper of a solar flare our way. The fire was so powerful it overwhelmed the spacecraft sensor that was measuring it. The sensor topped out at a whopping X28. But later, scientists figure out that the flare had reached a peak strength of about X45. One more thing that made the Halloween storms so scary was that they happened during a time in the solar cycle when solar activity is usually quiet. That's 2 to 3 years after the solar maximum. According to NASA statistics, just 17 powerful flares erupted from our star during that time. The Sun spewed out another X-class solar flare on the 5th of December 2006. It was an X9-class flare that disrupted satellite-to-ground communications and GPS navigational signals for around 10 minutes. That solar storm was so powerful it even damaged the Solar X-ray Imager instrument on the GOES-13 satellite. It sustained damage to several pixels of its detector. In February 2022, SpaceX experienced the terrifying power of our star when a devastating geomagnetic storm destroyed 38 Starlink satellites worth tens of millions of dollars. It happened shortly after they were deployed. Unfortunately, Starlink satellites are especially vulnerable to geomagnetic storms since they're released into extremely low-altitude orbits, between 60 and 120 miles. They also rely on their onboard engines to overcome the drag force and raise themselves to their final altitude of around 350 miles over the surface of our planet. The thing is, during a geomagnetic storm, Earth's atmosphere absorbs energy from the storm, heats up, and extends upwards. It results in a denser thermosphere, which means more drag, and it can be a serious issue for satellites. That's exactly what happened. The batch of newly released Starlink satellites didn't manage to overcome the increased drag and started to fall back, eventually burning up in the atmosphere.
Astronomers have discovered the most massive stellar black hole ever spotted in our home Milky Way galaxy. This newly found space monster is 33 times bigger than the Sun and sits 2,000 light-years away from us. Until recently, the largest stellar black hole found residing in our galaxy has been around 20 times as big as our star in terms of mass. As for the average stellar mass black hole, it's usually about 10 times as hefty as the Sun. Scientists from the European Southern Observatory's Gaia mission spotted the giant black hole after a star started to wobble while orbiting in that area. The black hole got the name of Gaia BH3. The proximity of this space object to Earth makes it the second closest black hole to our planet ever discovered. The nearest one is called Gaia BH1. It's hanging out around 1,560 light-years away from us. This uncomfortably close neighbor has a mass of about 9.6 times that of the Sun. It means that it's way smaller than the newly found black hole. Gaia BH3 is located in the Agila constellation. From Earth, it seems to have the shape of an eagle. Interestingly, astronomers didn't expect to find a high-mass black hole lurking so relatively close to Earth and remaining undetected for so long. Okay, we can probably admit that this stellar black hole is just a small fry compared to supermassive black holes like the one that dominates the center of the Milky Way. I'm talking about Sagittarius A star. This space giant has a mass of 4.2 million times that of the Sun. While a stellar black hole forms when a star collapses, supermassive black giants have their own ways of seeing the light of day. They are usually the result of mergers of progressively larger and larger black holes. We'll talk about that later. First, let's speak a bit more about how stellar black holes form. When stars near the end of their lives, they typically inflate, lose a lot of mass, and cool to form what we know as white dwarfs. Such massive stellar black holes as Gaia BH3 are believed to form when a star doesn't contain heavy elements and loses not so much mass over its lifetime. Such stars are called metal poor. Afterward, instead of cooling into a white dwarf, this star collapses into a black hole. The companion of Gaia BH3 is a very metal poor star. It suggests that the star that collapsed and formed BH3 was metal poor too. Astronomers know of about 50 stellar black holes in the Milky Way. Some black holes are larger than others. You see, the universe is filled with black holes. Some of them are sprinkled randomly throughout galaxies. Others, those giants we know as supermassive black holes, sit at the center of galaxies. While stellar black holes are usually just a few times bigger than the Sun, such space monsters can weigh from 1 million to 1 billion solar masses. But even though they're so much heavier than our star, they're packed into a relatively small area. On a cosmic scale, of course, the size of our solar system or so. Some astronomers think supermassive black holes could form by several stars colliding and collapsing at once, while other experts state that such space objects might have started growing several billion years ago. At first, a small seed appears somewhere out there in space, which then gradually increases in mass to form a black hole. This seed does it through the process of accretion, which basically means gathering more and more matter around itself. Besides the absence of any precise information about the formation of black holes, there's also the black hole information paradox. If a black hole has some mass, and as we know, these spaced objects have a lot of it, then, according to the first law of thermodynamics, it should have a temperature. And according to the second law of thermodynamics, it should also radiate heat. Stephen Hawking showed that black holes are supposed to emit radiation too. These days, this kind of radiation is called Hawking radiation. It should form at the boundary of a black hole, but after proving it, Hawking pointed out a paradox. If a black hole is capable of evaporating, some of the information it contains can be lost forever. The problem is that the information contained in thermal radiation emitted by a black hole gets degraded. It doesn't repeat any information about the matter swallowed by a black hole before. Such an irreversible loss of information contradicts one of the basic principles of quantum mechanics. Physical systems that change over time cannot create or destroy information. It means we must be missing something. Both physicists and mathematicians have tried to come up with different ideas, but they ended with pretty weird results. Some have even claimed that the universe could be holographic. It means that the universe that we know and love is actually the result of some mysterious interactions at the infinitely distant boundary. I told you, black holes are really strange. At the same time, we have definitely found space objects that seem to have the properties of black holes. For example, look at this image of black hole M87 star. It certainly looks like a physical object, but what if black holes don't exist at all? There's an idea that black holes are actually gravastars, a blend of gravity, vacuum, and stars. This theory was first proposed in 2001 by Emil Matola and Pavel O. Mazur. They hypothesized that at one point during the collapse of a large star, intense gravity might transform its matter into a new state. It's similar to what occurs when atoms are cooled to such low energy states that they start acting like a single superatom. When we speak of gravastars, a star might collapse to the point of the event horizon, or the point of no return, and then its matter is transformed into a new state. It exerts enough outward pressure to prevent the star from collapsing into a physics-defying singularity. In gravastars, an ultra-thin, ultra-cold, and ultra-dark indestructible shell surrounds heavily wrapped space-time. This new form of matter turns out to be very durable, but it's also a bit flexible, like a bubble. So anything that's trapped by the intense gravity of a gravastar and smashed into it gets obliterated and then assimilated into the shell of this bizarre space structure. One of the benefits of the gravastar theory is getting away with those messy paradoxes connected with information and singularities. But even though this idea sounds kinda cool, it doesn't explain the phenomena we observe. And we've definitely observed something that looks like black holes. On the other hand, look at this shadow. It isn't caused by the trapping of light in the event horizon. It's a slightly different phenomenon known as the gravitational redshift. It makes light lose energy when it moves through a region with a powerful gravitational field. So, potentially, it could be a gravastar. When the light emitted from the regions close to the alternative objects reaches our telescopes, most of its energy is already lost to the gravitational field, which causes the appearance of this shadow. And still, like with black holes, things get complicated when you add rotation to the equation. Many experts are sure that gravastars would not be able to remain stable during rotation. But wait, it gets even more bizarre. There are suggestions that the insides of gravastars could contain a series of thicker shells. Those are known as nestars, something like a matryoshka doll. Of course, these theories aren't perfect yet. Astronomers still have a lot of work trying to build functioning models. There's also a chance that both black holes and gravastars exist. But then, we've got another problem on our hands. How can we distinguish between the two? Some theories suggest that these different kinds of space objects should also emit very different gravitational radiation. It could allow us to figure out whether we're looking at a gravastar or a traditional black hole.
Electronic satellites suddenly go out of control. There are voltage surges across the globe. In some places, there's a complete blackout. Scientists have little data on this incredible solar behavior, so we're still unable to accurately predict how or when exactly the next geomagnetic storm will happen. One such event took place back in July 2012, but thankfully it missed us. Not by far, though, by a mere 9 days. Just to give you a glimpse of what nearly happened, I need to explain some astronomical basics. A solar storm is a series of effects we feel here on Earth after certain events occur on the Sun. Our star is nothing more than a huge ball of molten gases that are constantly moving around, so these events happen more often than you'd think. For a solar storm to begin, our Sun needs to emit bursts of energy. They're in the form of solar flares and coronal mass ejections. These two phenomena send electrical charges and waves of magnetic fields toward the Earth at an astonishing speed of about 3 million miles per hour. When these solar storms reach our planet, we can see northern lights display in locations close to the Arctic Circle. But they can also mess up satellites or other types of electronic communications. Some of these solar storms can be dangerous, and back in 2012, we came close to experiencing a very powerful one that could have had a serious outcome. The most powerful in as much as 150-plus years, based on research done by astronomers. But how did we manage to escape it? Did we have something to do with it, or was it just a pure coincidence? What we do know is that one of those coronal mass ejections did hit the Earth's orbit in late July 2012. Our planet had already left that specific location as it was on its scheduled trajectory around the Sun. So you might be asking yourself at this point, what if it didn't miss us? Turns out these intense solar storms are dangerous to all sorts of technological objects. Given we are now literally surrounded by electric objects, from our phones to our cars, try to imagine what would happen if they all stopped working all of a sudden. And here's how they work. Solar storms start with an explosion, or a solar flare. Then X-rays and UV radiation travel to our Earth at the speed of light. Some of the side effects? Well, they can include radio blackouts and GPS navigation errors. The effects can continue as minutes, or at times hours later, energetic particles reach our atmosphere. They move only a bit slower than the speed of light, but they can electrically shock the Earth's satellites and damage their components. Lastly, about a day later, clouds of magnetized plasma reach us as well. They can cause huge power blackouts, more or less paralyzing everything with an electrical plug. We might not even be able to flush our toilets, since most water supplies in cities use electric pumps these days. The effects of these geomagnetic storms would be different around the world, though. Solar storms are curious by themselves, but why do they affect some locations on Earth more than others? Based on recent research, geology has a lot to do with it. But I need to take you back a bit to paint you the bigger picture. Buckle up, because we're taking a trip in the time machine to a time when the moon didn't even exist yet. 4.6 billion years ago, our solar system looked a lot different than it does now, and that's putting it lightly. Hundreds of new planets began to form around the new sun. Planets like our own Earth, Venus, or Mars were still hurtling around the cosmos. Back in the 1970s, an astronomer named Donald R. Davis developed a theory that said the moon was born when another planet hit a newly formed Earth about 4.5 billion years ago. He also indicated that it might have been the size of Mars and later named this planet Theia. It's difficult to imagine what that impact might have looked like, even with the equipment we have these days. The astronomers suggested the giant impact hypothesis, trying to piece together this mystery. After running into our planet, the outer rocky layers of both Earth and Theia were projected into a circle of cosmic matter. Out of this debris, what we now know as the Moon was born. The Earth's core has apparently consumed Theia's iron core, that is, if it had any. Our planet also got into the position it occupies today. This way, it became more susceptible to geomagnetic storms. Back then, there was little to no information as to what might have happened to Theia, apart from giving us our only natural satellite. It took several years for a series of scientists to come up with an exciting new idea that revolutionized what we knew about our planet. What was left out of Theia is hiding under two continent-sized layers of rock deep within our planet. This theory is also one of the only explanations for why the Moon is so dry and doesn't have much of an iron core. But why is geology so important when it comes to geomagnetic storms? Well, that's because recent data revealed that the type of rocks below your feet can affect how well your city adapts after powerful geomagnetic storms. Some types of rock, like sedimentary rocks for example, generally have more space filled with water, which makes them electrically conductive. Other types of rocks are denser and have more resistance when it comes to electricity. Whenever such a storm happens, people living in the New England Highlands may have a higher risk of experiencing major disruptions. At the same time, those in the mid-Atlantic coastal plain have less to worry about, simply due to what's hidden beneath their cities. How did we know how scary these storms are? Well, this wasn't the first time it happened. Solar storms have dazzled the astronomer community for many years now. The most iconic event of this magnitude was the Carrington event, which happened way back in September 1859. It gave us a sneak peek of what the power of the sun is, to say the least. They named it after an English astronomer, Richard Carrington, who witnessed the solar flares himself. The power of that solar storm was something humans had never experienced before. The strong geomagnetic storm caused northern lights as far down south as the territory of Hawaii. On the morning of September 1, 1859, Richard Carrington made his way into his private observatory, located outside of London. He opened the observatory dome to have a complete view of the sky and directed his telescope to the location of the sun. He saw a bunch of huge dark spots that gleamed on the surface of our star. Shortly enough, Carrington noticed two enigmatic areas, intensely bright and full of white light bursting out from the sunspots. They disappeared 5 minutes later, but the effects carried on all across the Earth's surface. At first, later in the night, telegraph communications all around the world started to malfunction. Flashes of light started to burst from telegraph machines, disturbing the operators and even setting papers on fire. Brightly colored auroras started to appear in the nighttime skies all over the world, making confused birds chirp at night. Some people even began their daily activities, since they mistakenly thought the day had already begun. These days, our planet is laced with a mega information web, so the impact of such a solar storm would be even messier. Back in the 1800s, the telegraph system was just starting out, but this Victorian internet was an important way of sending news and private messages. Even in the United States, telegraph operators had noticed local interruptions because of thunderstorms and northern lights before. But the Carrington event and its effects were something they had never seen before. A lot of telegraph lines in North America became useless. One telegraph manager based in Pittsburgh even recalled that the currents flowing through the wires were so strong their platinum contacts were in danger of melting. Another example was that of a telegraph operator located in Washington, D.C., named Frederick W. Royce, who was hurt as his forehead touched a ground wire. Samples taken from the Earth's icy locations tell us that the Carrington effect was twice as big as any other solar storm experienced in the last 500 years. It's very difficult to imagine what the impact of a storm of that magnitude might be today. But based on a 2008 report drafted by the National Academy of Sciences, it might cost us between $1 trillion and $2 trillion in damages. There are things we can do individually to help reduce the amount of damage, though, like buying a generator or installing a backup energy supply. This can be either a solar panel or a wind turbine. More so, we can equip our houses with surge protectors that connect to our electrical panels and can save us from lightning and other power surges. The simplest solution of them all? Just unplug all the devices you're not using at any particular moment. If they aren't connected to a power source, they can't be affected by any surges.